So that's what we mean by scalable systems broadly. So on this slide, I'm going to talk about the CAP theorem and what it means. So there is this programming paradigm of ACID that we see in atomicity, consistency, isolation, durability. ACID gives us a very clear and a very, it's a classic clear computing paradigm, right? So if your database is up and running, you commit. If something is wrong, you just go back and say, okay, I can't do it. You write something to a data store and you immediately read it, you get the data back. So the consistency is really strong in a traditional ACID-based system. Whereas the CAP theorem, what it says is, if you have a distributed system, it's impossible for you to guarantee all three. You cannot get strong consistency. The system will not be available all the time, and the system will not be able to do partition tolerance. What we mean by partition tolerance is like anything that grows across the network, right? So unless you're running everything out of a single box, things you need to have network across in your system. So partition tolerance is something that's given. So what the CAP theorem says in short is you either get consistency or availability, and you have to pick one over the other. So traditionally systems, like if you look at any web system, right, making this choice is very important. So for example, if the user is going through a checkout and then he's trying to do add an item to his cart, your database is down for whatever reason, you are either going to go back to the user and say, I cannot take this right at this point. So it's a bad user experience. Or you go back and take the card from the user, but you don't persist it immediately, right? So your system in that sense is highly available. If at the same time, if for example an inventory system that's trying to read the number of orders that you have got so far is not going to get that data. So it's highly available, but it's not really consistent. So it's always you have to pick one or the other. So either you can go back to the user and say, I cannot take your addition of this item to your cart at this point. Or you take it, but then certain other systems will not know that you have actually taken this, as certain systems downstream, like for example your inventory system, your billing system, will not know that you have actually taken this item into the user's cart. This may not happen all the time. So it's something you have to understand. So what CAP doesn't necessarily mean you will get only consistency or availability. What CAP tells you is when system starts to fail, you can either, your system has to take either the consistency approach or the availability approach. So most web systems will try to go on the path of being consistent. So when we say consistent, we'll take the path of highly available and choose a path of what we call as eventually consistent. When we say eventually consistent, it doesn't mean like it will happen day after tomorrow or like 2 days from now or etc. Eventually consistent system, the order of consistency is sometimes like seconds or milliseconds or maybe minutes. Classic use case would be something like you go to your Facebook page and then you say like on something, right? And then your friend logs in, he may not actually see that you have given a like on a particular post. But if he logs in a couple of hours later or even like 2 or 3 minutes later, they'll see the like. So it's like but you as a user actually saw that like, but your friends need not, when they log in, need not immediately see that like. So it's an experience that you have to live with. So whatever you decide, either when you decide to go with a highly available system, it drives the user experience as well. It's just not like a technical decision, it's a product experience as well. So this CAP theorem was proposed by Eric Brover during, he was within Kutumi, which was eventually brought out by Yahoo. So this, it's called a theorem because a bunch of academics actually proved you can either get strong consistency or you get availability. So you have to either pick one or the other. So what it means is in today's system, you just cannot afford to do any kind of distributed transaction. So any application that tries to do distributed transaction is bound to slow the system, and it's bound to have a bad user experience, or it just will not scale. It just will fail. And the reason is this, right? So you need to have distributed databases because if something goes down, you're not taking the whole log down. For example, if say your inventory database goes down, your ability to take the cart item should still be there. But hopefully the inventory system comes back up at a point later in time. But because of that, you're not giving a bad user experience. You're still able to take cart rights. So distributed databases is a fact of life. So if you're building a high quality, lot of traffic production system, you cannot put everything in a single database. So distributed database is a reality and it's needed. But if you try to do a distributed transaction, that's when things get really slow down. So if you're trying to do if you're trying to lock tables across rows in tables that are in different databases, your system will bound to be really slow. Like any protocol that does it today, like two-phase commit or Paxos or quorum protocols. There are a lot of protocols in the literature. And these tend to work like if you are a 4-node, 5-node system. But if you scale it beyond like say 50 to 100 nodes, there is a lot of chatter between like even for the coordinator to come in and fix which protocol, which one gets to commit first, etc., etc. So you tend to slow your system really down. So your SLAs are way off. So when you try to do atomic transactions, all the transactions should be local. There is no concept of a distributed. I mean, you should try to take distributed transactions and abstract it in a different sense. So either you queue it or you invoke an operation or something that, depending on your flow, depending on the workflow, depending on where you are within that particular workflow, you have to accommodate distributed transactions, but not in a straightforward way by locking rows across databases.